Hello, calculus fans. Okay, so we've done quite a bit with taking a function and computing its derivative. We've done it in several ways. We've done it analytically by taking limits. We've done it graphically by showing a picture of a function and then using that to estimate what the graph of the derivative function looks like. We're going to go in reverse. Let's start with a function and find a new function, big F, so that big F prime is equal to little f. Okay, so our starting point is still the same. It's little f of x, but we want to find a function big F so that the derivative of that function is equal to f of x. And this thing has a name. It's called an antiderivative. And so we're going backwards. We're finding a function whose derivative is f of x. Okay, so let's do an example problem. Let's say you're given a graph of a function. It looks like this. And we want to answer a whole bunch of questions about an antiderivative of this function. Okay, so here are the questions that I want to answer. Where is that original function, big F, where is that increasing or decreasing? Where is it concave up or concave down? Where are the inflection points? And then let's sketch a graph under the assumption that big F of 0 is equal to 2. And the last thing I want to know is, how many antiderivatives does the function have? Okay, so let's look at part A. Okay, so we want to know where is big F increasing or decreasing. Now remember that little f is the derivative of big F. So wherever little f is positive or negative, that'll tell you where big F is increasing or decreasing. So you can go back to the picture, and it might be useful for you to have a sketch of the big picture, of the original picture, as we go on here. Notice that in the original picture, little f of x is negative on the interval from minus infinity to 0. So that's in this stretch in here. And then also from 1 to 2, so that's in this stretch here. So that's where f of x is negative. That tells you that big F is decreasing there. Then you can see where little f of x is positive, and you can see that that happens here and up in here. And that happens to be on the interval from 0 to 1 and from 2 to infinity. So we can say that big F is increasing there. Now let's talk about concavity. All right, so concavity of big F of x is asking where is the second derivative of big F, positive or negative. And now, right here, we can say that f double prime is equal to little f prime. So if we're asking where that's positive or negative, then really what we're asking is this question: where is little f of x increasing or decreasing? Now you can't tell for sure in the picture, but it looks roughly like little f of x is increasing on the interval from minus infinity to a half, and then again from 3/2 out to infinity. So we can say that big F is concave up on those intervals. And then we can also say that little f of x is decreasing on the interval from, looks like about 1/2 to 3/2. So we can say that the original function that we don't have, big F, is concave down there. Okay, so now let's talk about inflection points. This one's a little bit easier. The inflection points occur when the concavity changes sign. And that's going to happen at 1/2 and positive 3/2, because that's where the f of x changes from increasing to decreasing, which means big F changes from concave up to concave down and then back to concave up. So remember that the concavity of f of x is based on its second derivative, which is the first derivative of little f. Okay, so let's get a graph now. All right, here's a rough picture of what that function might look like. I've marked the y-intercept here about 2 units above the horizontal axis. I've also got all the features of being increasing, decreasing, concave up, concave down. So if you go back and match up with our properties that we had listed earlier, you'll see that it fits with the picture. So you might want to write down all those properties and compare it with this picture. And then the last question is about how many antiderivatives does little f have? Well, it turns out that there are lots of antiderivatives. All you have to do is take the one antiderivative we have and shift it up or down, and we'll get yet another antiderivative. It's basically just adding a constant to this function, and constants, when you differentiate them, disappear, so all of these functions will have the same derivative. So there's lots of different antiderivatives. In fact, you could say that there are infinitely many by just choosing different vertical shifting factors to put in. Okay, that's all for now.